I'm still unmuted. Okay. So I'm going to start with a brief review of what we talked about last week, and I'm going to immediately continue to the material that we haven't covered yet. So as usual, before we start, I've already started recording. I'm going to invite you to write your attendance. Wait a minute, not yet, not yet. Please write your attendance in the chat box. But for now, this time, I'm going to please request you to write your NPM because it was quite difficult to recap if you are you're only saying present. So please write your NPM there and I'll take your attendance from the chat. Okay, while you're doing that, remember this guy, these guys that we were introduced to last week. We have 4 new friends for continuous random variables. So we already looked at the random variables and we already looked at how we can define continuous ones, those that have a continuous value. But among those continuous values, maybe I should clarify that when I'm talking about continuous random variables, technically any measure, any one at all, that has a continuous value could be potentially defined as a random variable. But there are some special ones that we can study in more depth because of their common occurrence in real events. And we have selected these ones to study in depth: uniform, exponential, the Gaussian or normal random variables, as well as some derivations, some other distributions that come from this normal one. So I'm going to skip over number 1 and number 2 that we covered last week. I'm going to immediately continue to the normal random variable, which we actually already did look at last week as well, but I'm going to give you a brief review because the next part has a lot to do with this. So normal or Gaussian random variable has 2 parameters, and as usual, we have to write it with the correct notation. This is something that I would like to remind you to do in the event of any tests, to write your random variable using the correct notation. So here you can read this: X follows a normal distribution with parameters mu, which is the mean, and variance, sigma squared. Note that this is variance and not standard deviations. Don't mix it up. So since we have a mu, we know where it centers. And since we have standard deviation, we also know how far it goes out, to the left and the right. Obviously, my drawing is not perfect. Let's look at a better one. We know that we can move the means and it can shift, and we can also change the standard deviation, and then we can also change the height or the width of the bell itself. So some of you already noted on on the forum last week that it's symmetrical. Yes. It's also an asymptotic function, which means it never really does cross a 0. It goes very near to it, but it does not really cross the x-axis. And there are some other ones as well. We'll talk about that later on. So since we're talking about random variables, we also can define them in a uniform way, in the same way, by standardizing them. So just now we saw that we had so many different shapes of different variables. All of them are normal, but they all look very different. But if I want to have a standard way to calculate random variables, normal random variables, I can just standardize them by putting the middle, the mean, at 0 and using 1 as the standard deviation slash variance. So what we want to do is, instead of using different shapes that may have a different widths or different heights or different centers, let's just use one graph. So I can use some defined standard instead. So based on that, sorry, this should have gone before. So this is the standard normal distribution that we can compute some properties of. And what I would like to remind you of, I'd like to draw your attention to is this little friend on the bottom, the cumulative distribution function. We have also already studied that for any random variable, we can define them using PMFs, CDFs, and PDFs. But especially for the continuous ones, we can only define the PDF. Where is this? Where's my pen? Where am I? Not detecting my tablet. Anyway, the PDF and the CDF. But the CDF one is what is quite special with the standardized so-called standard normal variable. Why so? Because when I'm talking about the CDF, I am talking about the probability of my random variable being up until a certain spot, right? So anything up until a certain value. So since I'm only talking about the same shape of graph, which is the standard normal bell curve, then it can be standardized with this little symbol, which is phi. So phi z, or in other words, what is the probability my random variable is up until z? And hence I can define it using the PDF as follows. Why is this special? It's particularly special, this guy, because, hey, remember that the graph was the same for any variable I had. I can have any type of variable with any height, any width, any mid center, and I can map it, I can standardize it to this particular graph. So using the phi of z, I can, in theory, calculate the probability of my any variable, which is plotted to this one. And what is the probability of my random variable being any value from the left-hand side? Why the left-hand side? Because CDF is anything up to, anything less than and up to. So here, this is our phi z, and I can compute it for any, in theory, any value that is covered with by my bell curve. So since we know that the shape or the curve has some particular properties such as symmetry, I also know now that if I were to compute that area, so if I would, I really, really need my tablet. Why is it not detected? Give me a second here. Okay, we'll figure that one out later. So in order to compute this side, we already know due to the probabilities having, it must add up to 1. First of all, I could do 1 minus. But more interestingly, since I know this is symmetrical, I could also instead compute the probability of the other side. So I can change it to minus z, and I can compute that instead. Why is this useful? It's because the table that we already looked at last week as well will only give me the left-hand side values because it's a CDF. So if I were to ask you something on the right-hand side or larger, then you would normally not be able to compute it. You have to do 1 minus. But instead of that, I can also just flip it and I can compute the left-hand side in this case, and I can use the table as is. So what is the table that you're talking about, ma'am? So this is the standard normal table, which maps the phi z for any z. And as you can see here, the standard normal distribution written here is the table. These values represent the area to the left of the z-score. Don't get confused, it says area, but remember that when we're talking about the PDF or the CDF, we know that, the PDF, the integral is the area under the curve. So this is equivalent to the probability less than. So I mentioned that last week, I would like to use the same standard normal table throughout the course, because if you go out and Google it, there will be a lot of different standard normal tables that you can find out there. So after discussing with the other lecture team of statistics and probability, we have decided to use this file here, which should already be on your Skele page. Let's check. I have uploaded it on your Skele page. We have decided to use this as a standard. I have shared it on last week's material, the standard normal table taken from this link. And it's quite useful because not only does it give you the positive scores, but it also gives you the negative scores. So last time we used the one from the Ross book, which only gave you the positive scores, but I guess I don't want to make it too difficult for you. So let's use this one instead. It's a lot more informative. You can download it from the link that I have given you on Scaling. Okay, continuing on. So we can look up these values using the standard normal table. And if I were to compute anything, if I were to compute any probability from a basic normal random variable, I would need to first transform the normal normal random variable that I have, and I have to map it to the standard graph of the standard normal random variable. By doing so, I can then use the phi values and I can look those up using my my table. So now I'd like to leave you at one example that we already did this. We left off on this example last time. So this time I'm going to leave you to do this one. And then we're going to go into a problem that doesn't give you the numbers, but gives you a story and you need to translate it, and we'll work on that together. So go ahead and try this while I try to figure out these electronics, and I'll see you in about 2 to 3 minutes. Okay, good news. I figured it out. Good. Okay, guys. So I hope you have got some progress on this question. If you haven't finished it, don't worry. We'll go through this one together. So what I would like to emphasize here, first of all, is please don't forget that you have to, in many questions, you need to define your random variables. So let's remember that. In this particular question, you don't have to, but just in the spirit of remembering this step, I'm going to write that my x is a normal random variable that follows these parameters. And now I want to transform it. What is necessary is I need to change this so that I have z. And z is obviously, I don't really need to write this down, but it will follow a normal random variable with a mean 0 and variance 1. So to do so, I can compute the random variable as follows. When I need to convert, don't forget, when I need to convert to z, I need to minus with the mean and I need to divide it with the standard deviation. So in that case, I have 2, I have x, and I have 7. But I no longer want to use these values because these guys are following the normal random variable distribution. I want values that follow the z distribution. So I could do that instead, that instead, that instead. And if I go on and do that, we can compute 2 minus 3, negative 1, over 4, negative 0.25, less than. Don't be confused. What is this? I have my x. I minus it with the mean, and I divide it by standard deviation. Now I have z. That's it. And now I have 7 minus 3, 4, 4, 1. So now all of my variables are already, all my numbers, sorry, are already in the standard format. What can I do now? So now I need to utilize some theories that I already know. This, I'm trying to compute the probability of z being between these values. Remember, when we're computing between values, I could use the PDF, but since I want to use my table, I need to use a CDF. So I could translate this being z being less than 1 minus probability of z being less than minus 0.25. I'm going to take a moment here to justify this. We've already learned this before midterms, but just as a refresher, I'm going to reiterate one more time. Assume that's symmetrical, guys. I can't really do a perfectly symmetric one. So here, if I have minus 0.25 here, right? Then I also have, minus 0.25. And on the other hand, I also have 1 on this side. 1. This question wants me to compute the middle area here. In order to do so, I could compute this area here, all of this, which is the green one, z less than 1, and subtract it using this area here. I should use a different angle, sorry. This area here, which is z being less than minus 0.25. That will leave us with that middle area that I actually do need to find in this problem, this area here. Let's use dots. No, you can't really see that. You get what I mean. So now I could, instead of computing everything, now since we already have this in standard format and it's less than, this is also standard and also less than, then I can use the phi table. So this is phi less than 1 like that. This is phi minus 0.25. So what I need from the table is phi 1 and phi minus 0.25. I'm going to show you how to get phi 1 and I'm going to leave it to you to get phi minus 0.25. Let's go here. Oops, not that one. So I'm going to get phi less than 1. You recall, I go to my standard normal table and I need to get less than 1. 1 comma what? 1 comma 0, 1 comma 1, 1 comma 0, 0, right? Because it's just 1 if I recall correctly. Yes, yes, it's just 1 here. So I only need to find the 1, which is 1 comma 0, 0. And this is the value that I'm looking for. 84134. 84134. 84. See, I don't remember. 84134. And anyone would be so kind to look at the table and give me the phi for minus 0.25?
Miss, we can't hear you.
Since when?
Since
Sorry.
you asked the
Okay, so I hope it's not from the beginning of the question, but I hope it was since I asked you to check up the values. Please correct me if I'm wrong. Okay, so Afriza's was wrong, right? You're yet okay. So we have 0.40129, 40129, and go ahead. You guys have the usage of your calculators. You can check this value here. There you go. I already did it. But this part is what I want to emphasize for you. So we had decided to give you access to to use the table that has minus values, negative values. But in the case that you do not have access to a table that gives you negative values, don't fret, because actually you could still compute it. So here we have phi of minus quarter or minus 0.25. If you don't have access to a table that gives you explicit values of explicit probabilities of negative values, you still can compute it using 1 minus. So do not forget that you can also use the law of probability to compute the phi or the CDF. Any questions? I'll give you guys some minutes to try to take that in and have questions if there are any. Not yet? Okay, then I will show you another problem which you first need to translate to the correct notation. So I'll give you some time to do so, read the question, and drink break for me. See you in a bit. Okay, anyone? Would anyone want to try? Can you guys annotate? You actually can annotate. Does anyone want to try? I bet no one is going to admit that they have a digital pen now. Anyone? No? I see a lot of people smiling, but nobody's holding up their digital pen. So I don't really know if you guys have one or not. Okay. Oh, well, I'll do it then. But you guys have to tell me the values, okay? You can either do it through chat or unmute yourself. Okay, I'll do the writing. You guys help me out with the values. So, good practice is to define the variable first. So I'm going to use, as usual, x. So in this case, I have x, which is the battery life. And in this case, x will follow, anyone? It's gonna take a long time. Writing on the chat, yes?
Normal distribution with
And?
the mean of 3 and variance of 0.5 square.
0.5 squared, great. Don't forget that it's given standard deviation, but you need to write the variance when you're defining the random variable. So that's great, that's perfect. Okay, so here we have our random variable. And now what I need to do is compute the probability that this battery life, x, is less than 2.3 years. To do so, I then need to transform x into z. So what I can do is do x minus, what do I need to do? Minus what? How can I transform this? Anyone? Anyone? Sorry, your face is coming up on my screen, so I'm going to call you out, okay? Seto, can you help me out? Seto, what do I need to do here? Minus? I need to minus the mean.
Is it 3?
Yes, that's right. We need to do minus 3 both here and there. And we need to divide it with the standard deviation in this case. So we will have this side, don't worry about it. We're transforming x to z. That side 2 comma 2.3 minus 3, 0, negative 0.7. Am I right? Yeah. 0.5. And thus I can transform this. We already have z and we already have less than. So this is phi of blah, 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 minus 1.4. And you guys can look this up on the table. So if we are going to translate the second one would be the probability that the battery lives more than 3.5. And the last one is the probability that x lives between 2.5 to 3.5 years. Anyone would like to help me out? One more thing. So notice that here I say less than 2.3 years, more than 3.5 years, between 2.5 and 3.5. What happens if I do that? Does it change anything? Does it? Does it? Remember? Will it change? There's a chat coming in. No, it will not change. That's right, because you guys have already written correctly on your midterms as well. The area of a point is 0, so it will not affect the total probability. Okay, 1 minute thinking process. Any questions? Okay, so no questions. So I'm going to continue. So allow me to remind you that up until now, what we've been talking about is, excuse me, is a repetition of, right? Lesson learned: when coughing, do not drink coffee, drink water. Okay, so up until now, what we've been doing is a repetition of what we already learned last week. We already talked about the normal random variables, but I thought it was quite important for us to go over it one more time to make sure no one is still confused, because what we're going to study for the next 3 weeks will be will need a very good foundation of the normal slash Gaussian distribution. As I already mentioned, the reason why this is very important is because most things in this world, most events, could be approximated with a normal distribution, because obviously it will never be a perfect normal distribution, but we can use it as an approximation. So much so that not only is the normal distribution itself used to model things in life, but also different combinations of normal random variables. There are 4 cases that can happen. So first we have linear function of linear function of a normal random variable. So I have a normal random variable, one normal random variable, and I know that I have a second linear function that is a linear combination. No, sorry, linear function of, I have to reserve the word combination, sorry, linear function of this particular normal random variable. And thus, I can compute the new random variable distribution as follows. On the other hand, if I have 2 independent normal random variables, I can also sum them up in this case. So if previously we only had one, and then we added them, we multiplied with a scalar, and we also added it with another scalar, we have the left-hand side. On the right-hand side, I have 2 different normal random variables, and I want to sum them up. Note that they must be independent. The third one is a linear combination, not the same as a linear function previously. So here is if I have multiple independent normal random variables. So if I have x1, x2, and so forth, and I know they're all independent, and I have constants a and b, and thus I can combine all of the known independent RVs into one linear combination. And lastly, it's quite straightforward, but if I also have a series of independent normal RVs, I can also compute the distribution of their average as follows. The mean does not change. What changes is the variance and standard deviation. As an illustration, I'm going to give you an example here. You can go through the full computation through the slides, but I'd like to decipher the question into the correct notations together. Here we go. Okay, guys, thoughts? Go ahead through chat or unmute. What do we have here? Any thoughts? Oh, I'm going to actually show, okay, no. Anyone? No? Anyone doesn't want to share their opinion? Oops. Okay, so let's try to translate this together. We have the information of yearly precipitation, and I know that X is the precipitation. But I also know that this is the precipitation of every year. If I want to talk about the specific year, that means I need to define it as Xi. So the precipitation of year I would be Xi. And I know that Xi follows a normal random variable distribution with that mean and this variance. Variance must be used in the notation, not standard deviation. So if I know that every year Xi, so year 1 is X1, will follow this normal distribution. Next year, X2 will follow the same normal distribution. Thus, I can compute the total precipitation during the next 2 years as X1 plus X2. I want to know the sum, the total precipitation over the 2 years. So I would like to point out here that in another class, in the regular class, there was a question, why can't we note this as 2x instead of x1 plus x2? So what we have decided, what we think is the correct explanation, if you guys have an opinion, please feel free, because it's a discussion. Don't worry, I don't know things too sometimes. Is because of the fact that I've already mentioned just previously that obviously things that occur in real life aren't actually a perfect normal distribution. There will be different deviations. So in this case, every year, the precipitation is not exact. It's not the same normal distribution every single year. It might change a little bit the standard deviation, it might change a little bit the mean and so forth. But in order to model any type of physical thing, you can't really do that, because like you can't even model light correctly. You need to find the closest approximation. And in this case, all of these years can be closely approximated using this particular normal variable. And thus, when I'm saying x1 plus x2, I'm acknowledging that x1 and x2 may differ. So I'm not assuming that they are 2 times of the same thing. So in that case, since it's x1 plus x2, it will follow the rule of the sum of independent normal RVs, which if you go back and check the slide later, you can figure out that the x1 plus x2 can also be defined following a normal random variable of mu1 plus mu2 and variance 1 plus variance 2. I think that's correct. So in here, I know that the sum x1 plus x2 will follow n of, I already computed it, I have a cheat sheet down here. You can correct me if I'm wrong, 24, 16, and 19, 22. And thus, the question that's asked here is, find the probability that the total precipitation during the next 2 years will exceed 25 inches. So what is the probability that x1 plus x2 will be larger than 25? And so forth. You can continue using the same steps that we already tried in the previous questions. Let's see here. I have already computed it on the slide as well, which you can download. And as you can see here, it's also the same. It's the same case. What's the probability that the sum is more than 25? Please note that here the precision is not the same as the precision given in the book, in neither books. So Ross only gives you 2 numbers behind the comma, and the one that I just released to you has 5 numbers behind the comma. And if you recall in your midterm, I asked for most computations to be done with 4 digits behind the comma as your precision. So let's just keep it at that. That if, unless specified otherwise, please try to adhere to the 4 digits behind the comma standard, just so that it doesn't end up with different results of computations, because correcting it is quite a nightmare with different precisions. Okay, so that's the first one. And for the second one, I'll give you a chance to read through it and let's translate it together. Okay, while you do that, I'm going to address the question Afriza has in the chat. Would you care to say it out loud to the class so everyone gets the gist?
So to my understanding, with the question, the yearly precipitation in Los Angeles is a normal random variable. I think it is assumed that for each year, the mean and the standard deviation is the same. Thus, I think it would be better to use the 2 times mean and variance as you said, each year the mean and variance would be different, right? In the real case. So when we use 2 times, then the variance would be bigger to accommodate those assumptions. So I think it would be better rather than use x1 plus x2 since it would leave us with variance equals to about 19.
Okay, let's look at the answer here. So this is already a larger variance, is it not? It's 2 times the.
No, as with 2 times mean and variance, you would get about 38.44.
For which one? For variance.
For 2 times variance, it would be about 38.
Okay, so that's if we use 2x, right?
Yes.
So we assume it is a linear function. Like, so it's, sorry, let's go back here. So instead of using the one on the right, we're using the one on the left here.
Yes.
Are you talking about that? Okay. So this is the exact same discussion that has come up during the regular class, which I try to preempt before anything. So as I mentioned before, at the moment, we are following this x1 plus x2 based on the logic that it's not the same every year. And I honestly do not really have an explanation why yours wouldn't work, because it also makes sense. But as far as we've looked through, we have 2 different books that we've been using as a reference. Most ones that use a linear combination or linear function gives it to you explicitly. Like, for example, I know x follows some distribution, and I know that y is 3 times x. So we know it for sure that it is 3 times a 3 times multiple of that one. But in this case, because we're talking about total precipitation, we can assume that the first year and the second year are independent of each other. And the key word here is independent. And thus, we do not assume that the second year is a multiple of the first year. And thus, we are following this x1 plus x2. But yes, I acknowledge the logic of your argument as well. And allow me to put that on hold for a sec, okay? And if anyone else also wants to argue in your favor, go ahead, because as I mentioned, I don't really know of the exact answer why yours could not be correct. So yeah, other than that, I don't really have an answer yet for you. So okay, anyone else? Okay, not yet. So obviously the next one, oh, not this one, sorry. The next one is very simple. What's the distribution of the average tomato plant? If we know that one follows this one here, this is just an easy example because it's an average. We know that I need to divide it by 20. Okay, straightforward. It's an average. Okay, anyone else? Okay, now you're gonna make me have to study a little bit more tonight, Afriza.
I'm sorry, Miss.
No, it's okay. Okay, so if there are not any questions, I'm going to move on now to this next one, which I'm not going to go into much detail because I want to start the next material ASAP. So the basic thing is that, remember when we had the Poisson random variable, we could use it to approximate the binomial random variable. The main reason is because the binomial random variable is discrete. So when I'm computing probabilities, a lot of the time, since we are given the PMF, I have to sum up all of the PMFs of every value. So instead of doing that, I could use the normal approximation to the binomial distribution as well. So one point that you need to recall is that since the normal random variable is continuous and the binomial random variable is discrete, you need to have some tolerance plus 0.5 and minus 0.5 to account for the continuous values that get rounded up to the discrete points. So in order to do so, I'm just going to prove to you that in this computation, we use a binomial distribution B, 16, and 0.5, which we are approximating using N, 8, and 4. Where does 8 and 4 come from? This is N, this is P, this is NP. I believe this one is, let me cheat a bit, NP 1 minus P here. And as you can see here, if I use the binomial distribution, I get this value. And if I use the normal distribution, I get this value. Of course, this is an approximation, so it's not the exact same answer for both. Why is this useful? I'm going to give you an example on a question where it might be a lot easier to use the normal distribution instead of the binomial one. So in this case, when I'm computing this question, I have a x that follows the binomial distribution, and I want to know what's the probability that y is less than and equal to 190. That means if I'm going to use this discrete binomial random variable, I need to sum up plus y equals 1 plus until y equals 190. And inside of that, remember the binomial equation, I believe it's a combination. So in here, I need to do 190 over 0 and so forth and so forth. It's quite a tedious computation, something like that. So instead of doing this tedious computation, then maybe it's quite easier for me to do an approximation using a normal random variable as follows. Sorry. This is not B, this is N. Typo, sorry guys. Following N, and thus I can get this answer quite easily. I have a table, I can just look it up. Any questions? Not yet? Okay, I'm getting pessimistic that we can finish the distributions of sample statistics. So I think I'm just going to intro it to you later at the end, and we can go into that next week. Because for this chapter, we still have all of these friends. Okay, I'm going to give you around 1 or 2 minutes to wrap up your thoughts on the normal distribution that we already talked about up until now, because now we're going to get dirty, because we're going to play around with the normal distribution. Okay. Okay, hello. Am I still connected, guys? FY, because, okay, because a lot of you just froze on my screen just now, so I don't know if it's you or me. And since more than one person is frozen on my screen, I thought it was me. Okay, my voice is still coming across? Everyone's okay?
Yes, Miss.
Okay, good. Ooh. Okay, so now we already have established the point of the normal distribution, in parentheses, the standard normal distribution, which is obviously a little bit more useful for us compared to the others. So the thing, oops. Sorry guys, just a sec. I pressed something unintentionally. Okay. Okay, so now we have different distributions that the whole reason that they are there, that they have come about, is because someone is trying to remodel the normal distribution itself to some type of derivation. As I mentioned, almost everything in the world can be defined more or less following the normal distribution, most things. But obviously, as I said before as well, this is an approximation. Nothing is actually following a perfect normal distribution. So keeping this in mind, some people thought that, then why don't we define some variations of the normal distribution that can probably model the probabilities better. And we have chi-square, chi-square. In Indonesian, it's chi-square, but I think it's chi-square in English. I'm not so sure. Please correct me if you know. Chi-square and T distribution and the F distribution. We're going to go through all three of them, but I would like to emphasize that what's more important, that's most important for us in this course, will be the chi-square and T distribution. The chi-square one is because it's very often used for chi-square analysis, which you might learn in later courses, not in statistics and probability, but maybe in data science later on. And the T distribution is also very useful for your later hypothesis testing. The F distribution is more like you should know about this, but it's not going to, you're probably not going to meet it again. Later. You're probably not going to meet it again later, at least not in Statprob. So let's go into the math, shall we? The chi-square, so after this I just said it should be chi-square. Okay, so I'm going to change now. So the chi-square distribution is when we have independent standard normal random variables, which were x, and I can define this x as a sum of squares, of different standard normal random variables. So don't forget that here we're having z1, z2 until zn. Each z here is standard, but x is not standard. Instead, x is a chi-square distribution with n degrees of freedom. What's this n degrees of freedom, you say? It's the number of independent standard normal random variables that are squared and summed up to make up x. And thus it gives us this very quite complex notation. X follows a chi-square distribution with what's it called? The degree of freedom of n. This 2 up here is a square, so it's always going to be there. What will change is this n, which is the degree of freedom. So I'm going to focus you on a couple of terminologies here. So x is a chi-square random variable with n degrees of freedom. So its shape can be like this. Here it's 8 degrees of freedom. The shape will change based on the degrees of freedom. So say this one is 8. If my degrees of freedom is 3, it'll be different, and so forth. And for any value, any alpha between 0 and 1, note that's between 0 and 1, the quantity is to be defined, x squared is as such that x is the probability that x is my random variable is larger than this particular point equals this proportion. What does this mean? This means that the probability of my random variable being in this area here is equals to alpha, and this particular point here, which is also known as the critical point, is where I draw the line on the graph. So I'm going to repeat what we just wrote here, which is, this is the formal definition. I'm going to use my own words to explain it a little bit easier. So as I mentioned, we first have one parameter, which is the degree of freedom n. The degree of freedom will change the shape of the graph. So let's say I have a degree of freedom of 3, for example, and the shape is something like this. It's not really, but I'm just making it up. So I have a degree of freedom n. If I have a degree of freedom 3, I know that the shape will be as such. If I have a degree of freedom of 12, I know that the graph will be something else. So that's the first point of chi-square distribution, the shape of the graph. Next, if I want to know the proportion of the data to the right, so I have a couple of things here. If I were to know the alpha, like for example, I know the alpha is 0.05, for example. I want to know, this is a proportion, right? So this will be equal to something like 5%. I want to know if 5% of the population lies on the right-hand side of a certain value. Where I draw that line is the critical point of the chi-square. So if I want to know based on my distribution, here is the, sorry, I should have used the red one. Here, this distribution is the chi-square using the degrees of freedom n. This is my graph, and I want to know, hey guys, where do I need to draw my line if I want to know where 0.05 parts of my population is on the right-hand side? So it would be this particular line, for example. And if I draw this particular line, this is where this area on the right-hand side is corresponding to 0.05 of my population, or 5%. of my population. On the other hand, if I want to know, hey, I want to know where do I need to draw my line if I want to know where 0.95% of my population lies on the right-hand side of a certain value. Oh, then I need to draw my line here, maybe, for example. And thus, this part here is where I draw my line of 0.5, comma, n is my degree of freedom. So here it's n. And I know that this area on the right-hand side will correspond to 0.95 of parts of my population, or 95% of my population. So here I want you guys to pay attention to these three values that are intertwined. N, or the degree of freedom, will change the shape of the graph. Alpha, or the proportion, is the proportion of the population on the right-hand side of a certain line, a certain point. And the critical point itself is what we're looking up on the table. So where do I draw my line so that on the right-hand side of my line has the corresponding proportion that I'm currently looking for. The chi-square also has an additive property, which means that if you combine a couple of them, it will follow this rule if you put x1 plus x2. So let's first look at the table here, and then we're going to interpret it as which is the critical point, which is the proportion, and so forth. So here I have a question for you. Please find the critical point of this chi-square distribution with alpha 0.05. So I want to find 0.05 proportions of my population, and my degree of freedom is 15. So this is my degree of freedom, and it's 15. So based on this table, you can see obviously that the degrees of freedom is here. So I need to find 15. Where's 15? Here it is, 15. And I need to find 0.05, which is over here. So if I draw the line correctly, 15 is here, right? Yes. So this equals 25, the point of 25. What does that actually mean? So if I draw it back to the graph, what I know first is my degrees of freedom, I have 15 of them. So maybe the shape is something like that, maybe. Next, I know that I'm trying to find the alpha, or the proportion, is 0.03. So 0.05. I want to draw a line anywhere along my x-axis. I want to draw a line so that wherever I draw it, on the right-hand side of the graph, we have 0.05% of the, 0.05 parts, or 5% of my population on the right-hand side. And in this particular case, I know that the place where I need to draw my line is at 25. Pause. Any questions before we go into a problem? No one yet? Okay, so hopefully no one will get confused about the critical point versus the alpha, because the alpha is the proportion, or the probability under the curve, or the portion, and 25 here is the critical point where I'm drawing my line. So this might be all clear when we're only talking about the numbers, but now we have a problem. Here we go. Okay, so we need to know a little bit about the coordinate plane here. So this is, you need a little bit of math to do this point. So if I have a three-dimensional space, imagine I have three axes like this. And this is x1, this is x2, and this is x3, for example. I have a point somewhere in the space, and I need to find it. This is it. So obviously here I would have, So obviously here I would have a point that is the actual point and somewhere that I'm targeting. So there will be a short error between these 2 points. And such we know when I'm trying to compute a distance between 2 dots on a Cartesian space, I know that the distance would be following the Pythagoras. What is that in English? I've never taught calculus in English, forgive me guys. It'll be something like that. Or in other words, d squared will be x1, x2 squared plus x3 squared. So here comes a little bit of trickiness between the x's and the z's. So this point here is taken from the Cartesian coordinate that I just explained just now. Down here is how I need to transform x. As we know here, it's a normal random variable. Sorry, I forgot to write this. Xi is n, which follows 0 and standard deviation 2. I want to change these x's into z, which is a standard normal variable. And following the standard equation, I know that each z should be equal to x divided by 2. And thus, on the other hand, I can also write the same equation, x1 equals 2 times z. And thus here, this is why we have this here, because from this left hand d squared x, I want to change it to z. So what happens here is when I'm trying to change it to z, then I have, when I have z here, I have 2x and so forth. And where's my computation? Yes. So here I have the 4 comes from the 2 underneath that gets squared up and moved to the right hand side. And thus I have a chi-square that is which has a degree of freedom of 3, and it has to be larger value than 9/4, which is around 2.25. And if you go through the table, you'll find that this critical point is corresponding to 0.5222. Note that sometimes you will not be given the alpha or the proportion that you're looking for. Unless specified otherwise, always assume that the alpha is 5% or 0.05. Pause. Any questions? Not yet? Okay, let me finish off all the special ones then. So following the same logic with the chi-square, we also have t distribution, which is some sort of variance from the normal distribution. So here, it's the same like the normal distribution. It's symmetric symmetrical left or right of the 0 point. And as n, the degree of freedom, becomes larger, it will be very similar to a standard normal density. Notice here that the tails, or the left-hand sides, these ones here, are thicker than normal standard normal deviations. So if the chi-square was equal to that, the above here, then for a very large n, so for the t distribution, it is a chi-square divided by some degree of freedom. And here we know that if we have the standard, we can also change it from this equation here. We can change it back to this one here. So what I would like for you guys to make sure you understand is to differentiate the problem, the distinction between the critical point, which is where we draw the line, the proportion, which is the area under the curve on the right-hand side, this. And why is this necessary? Because usually when we are trying to do the hypothesis testing, we don't really want to know what most of the people are doing. Obviously, most of the people will be falling under here. Most people are normal. But what is more interesting to us when we are trying to test our hypothesis is to find out if people are not following the norm, or in other words, in these tail areas. This is why the t distribution is, as a variant of the normal distribution, is used for hypothesis testing in cases where we do not know that the population is normal. If we know that the population is normal, then we'll just use the normal distribution. But when we do not know, we do not dare to assume, and thus we can use the t distribution instead. So what I would like for us to first realize is to look at the table. So obviously here we have a t distribution with this is the alpha, and this is the degree of freedom. Once again, the degree of freedom will determine the shape of the graph, and the alpha is the proportion that I'm trying to look for. So let's go and see the tables. Oops, nope. Let's go and see the tables that I have. Can you see that here? Oh, that's the standard normal table. T distribution, let's use that one. So just now the question was to find, see, I'm already lost, is to find T 0.025 and degree of freedom of 9. So let's go there. We need 9 degrees of freedom, and our proportion would be 0.025, which is this one here, 2.262. So we know that the answer here is 2.262, but what does that actually mean? So based on our table, we know that this is I've already forgotten. Anyone? What was it? 2.262. 2.262. So let's translate this meaning. On our graph, I have 9 degrees of freedom, which means that maybe it's shaped something like that. Maybe it's symmetric, it's along 0, but the shape can be different. And I know that I want to find where 0.025 of my population lies. Where do I need to draw the line? So here, this is my critical point. Apparently, if I want to divide my graph and find where 0.025 of my population is on the right-hand side, where I need to draw my line is at 2.262. Now, for the second one, I want to know what's the probability that T with a degree of freedom of 12 is less than 1.4. let's try to dissect it using the same graph. The graph logic. So here we have a t distribution with degrees of freedom of 12. So let's say something like that, right? It looks something like that. I'm making it up. I don't really know what it looks like. And what is the probability of t, my t value, my t distribution being less than and equal to 1.4? What am I asking here? So here I have 1.4. What is the probability of my t distribution being on this side, less than and equal to? So note here that on the first question, I know the proportion and I'm trying to look for where I'm drawing my line. I want to find my critical point. But on the second part, I need to find, I'm already given where I'm drawing my line, but I want to now know the proportion. So I have my line, but I want to know the proportion. So let's go back to the table and I want you guys to take a moment to think about, how can I find that answer? So I want, instead of giving you the proportion and asking you to find the point, the place I need to draw my line, I'm giving you the other way around. I told you where my line is. I want you to figure out the proportion. Take a look at this table and I want you guys to give me, what's your inkling? What do you think we need to do in order to find the answer for number 2 here, which is, I'll write it down on this side so you can see. There you go. I'm going to give you guys around 2 minutes to think about it. Please remember that the concepts of critical points and the proportions. I'll give you a second to think about it. If anyone has an idea, go ahead and unmute your microphone or write it in the chat box. How do you think we can solve this? Anyone, any ideas? Can I call you out then? Anyone? Oh, I have a chat here. I think we find the value of alpha for the degrees of freedom 12 that is less than 1.4. Okay, Bagus, can I ask you to help me out here on the table? How can we do that?
For the degrees of freedom 12, I think the value
so we're here, right?
Yes.
Okay.
It's
yes.
for 0.1, I think, because that is the only value that is less than 1.4.
1.4. So what you're doing here is you're looking actually at the entries, right? The data points of the table, right? So you're looking it up the backwards, right? So usually we're looking up based on degrees of freedom and alpha, but now you're looking up the values and you're trying to find the correct correspondence of alpha, right?
Yes.
Yes. So exactly that, Bagus. Don't you think that's quite a difficult task though with this table?
I think no.
You think no? But if I
personally.
want you to give me an exact value, do you think you would be able to give it to me?
No, because I think not every value is exact.
Like for example, in this case, if I were to give you T12 is less and equal to 2.1. No, that's too easy, sorry. 2.4, for example. It's a little difficult for you to find because on here, 2.4 would be somewhere between this one and this one, right? Somewhere between this and that. So it should be somewhere between 0.025 and 0.01. So I'm going to actually give you the correct answer, Bagus, for this question. So the correct answer for the second part is 0.9066, which you cannot find this, right, on the table. It's impossible for you to find on the table. So this was a little bit of a trick question because I will not ask you this question on any test because you can't find it on the table. So what I would rather you know, all of you would know, is I want to make sure that you guys really do know what is the critical point and what is the proportion we're talking about. If you do want, if I ever ask you to please compute the exact values, I won't do it on the test, but you might need to do it for your group assignment. There is actually something here that I can show you. I also gave this to last year's class, and you are allowed to use these. These are online tools. So I'm going to show you something here. So there is you can actually compute it because from the table, you can't find it. You can find so many p-value distributions. So apparently, I just figured this out recently as well. Why is my internet being stupid? But here, so what I can do using these calculators is to calculate that exact opposite. Because from the table, you'll only get a rough estimate, right, Bagus? You can estimate that it was 0.1 just now, but you cannot get an exact value. So for this just question that we just did, if I have 12 degree of freedom and I have 1.4, then I would get 0.01 tail if it's one-tailed probability and two-tailed probability. So here we have a spoiler alert to your hypothesis testing. You're going to need the difference between one-tailed and two-tailed in a bit in the hypothesis testing part of this course. So I would urge you not to worry too much about these distributions now. My target for now is for you guys to be very clear as to where the critical points are and where the proportions are. And we can go from there to the next chapter. Lastly, I'm going to close with the F distribution, which once again is a variation or a combination of the chi-squares. And here we have 2 degrees of freedom, which you can look up as follows. We also have a F table somewhere here. Where's my F table? F table, I have an F table. Here we have an F table with the 2 degrees of freedom, degree of freedom 1 and degree of freedom 2, and a certain alpha. So you have to know which alpha you're talking about. So all of these 3 derivations, what I want you to leave with at this point of the course is a clear idea of the lines and the proportions. We are going to move from there in the hypothesis testing, but I can assure you that I will not actually ask you direct questions like compute the chi-square or something like that. I don't think that's the point. The point of knowing these distributions is to apply them later on in the hypothesis testing. So Bagus, it's clear, right? From what your answer, you can approximate it. But if you want to know the exact value, you have to use those online calculators. Thank you very much for your participation. That's the exact answer I was looking for. Any questions? Not yet? No? Okay, guys. So I underestimated the complexity of these normal random variables. I was hoping for us to start a little bit, on the distribution of sampling statistics, but I do not believe we will have time to do so. But I have already published the materials on Scale. I implore you to first do your exercises for the normal distribution, to take a peek and get a head start on the distribution of sampling statistics. I'm not going to cover it today because that will just mess your heads up a little bit too much for my liking. But I do want to give you one intro to what we're going to talk about in the distribution of sampling statistics, so that if you do have time to look through the slides, you're not that lost. So instead of going through my slides then, I'm just going to draw the intro for you, and we'll go through it in more detail next week. So we have a population, right? This is my population. I'm going to study something about UI students. Obviously, I will not have time nor resources to actually ask every single UI student. Instead, I'm just going to ask 30 UI students of cohort 2020. I'm taking these 30 people from the entire population. So if this is the population, this is the, anyone?
Sample.
Exactly. This is my sample. So up until now, we've studied a lot of things about the sample. But as we already mentioned from the beginning of the course, the main point for me is by computing my samples, I want to know something about the population. So this is the first step of our inference statistics. From the sample that I take, I want to be able to understand something about my population. So from the sample, what can I do? I have 30 points here, 30 data points here. Just assume there are 30. From my 30 data points, I can compute my mean, right? Oh, sorry, not mu. I have to rewrite that. My apologies. Mu is the population, so that's my mistake. I can compute the sample mean, right? I can also compute the sample variance. I can compute it using just the 30 students that I asked, not the entire population. So now we already know that the concept of random variables. So here, although I do not know the mean of this population, nor do I know the mean of the variance, but I can understand something about both the mean and variance of the population, because if I assume that the mean of the population is a random variable following some sort of distribution, I don't know what it is yet, as well as the variance is some sort of random variable following another distribution that I don't know yet. That means if I had taken a small sample here and computed the mean and the variance, then this mean is part of the bigger mean. This variance is part of the bigger variance. And I can assume that this is also a random variable. Oh, I should write it like that. This is also a random variable that follows the same distribution as the mean mu here. And this is also a random variable that will follow a certain distribution too. So this is distribution 1, this is distribution 1, this is distribution 2, and this is distribution 2. So in this next chapter, what we are going to do is, by computing the sample statistics, we want to estimate the underlying distribution of the population parameters. We have the sample statistics. So if you remember, statistics to a sample is a parameter to a population. So based on the means that we can compute, we cannot actually compute the exact values here, but we could compute the underlying distribution that it should follow. So I would know that it's Bernoulli, for example. I would know that it is Poisson, although it will not be. But that is the basic mindset that we have in the next chapter. I'm going to end with a short question a short question session about this part only. So this is a very brief introduction as to what we're going to study next chapter. Any questions? Okay, although you don't really know how to do it yet, do you have a good idea on what we are trying to do next week? I haven't gone into how to do it yet, but I have gone into what we're going to do. All good for now? Okay, then I will leave you with the exercises on Scale. Please do them. They are going to cover both all three, uniform, exponential, and normal random variables. And keep your eyes peeled until the end of this week for announcements on the grades or the group assignment that will be released at the end of this week. If there are no more questions, then I'll leave it at that. Don't worry, Afriza, I remember your question. I'll have to bring it to the lecture team once again. So hopefully I'll get back to you on that. Okay, so if there aren't any questions, I guess I'll end it there at this messy scribbling of mine, and I'll see you guys next week.
Thank you.